In this lab, we're going to be titrating a store-bought hydrogen peroxide to verify the claim that it's 3%, which is 3 milliliters for every 100 milliliters of volume. To do this, we have several steps to go through. Being a redox titration, we need to make sure that our titrant has not either reduced or oxidized, depending on what it is. In our lab here, we're going to be using potassium permanganate, which is a strong oxidizing agent when acidified. Nevertheless, it could slightly change its concentration over time, and because this is a solution off the shelf, we need to standardize our titrant. So that concept of standardizing a titrant involves creating a solution from scratch of something called a primary standard. And in our case, our primary standard is going to be an iron 2 ammonium sulfate complex. The mass is calculated based on the concentration of this solution to be 0.05 moles per liter for a 100 milliliter volumetric flask. So part of your lab, of course, is to calculate the mass required of this primary standard. And then we're going to create the solution and then use that solution to titrate our titrant in order to calculate the titrant's concentration. Once that step is done, that step being the standardization, then we'll go ahead and titrate our actual unknown, which is our peroxide. In the standardization step, the titrant is going to be in the burette, but the titrant is going to be considered our unknown. The primary standard is going to be in the flask, and our primary standard is going to be known, as it will be calculated and then created from the mass. Once that's done, the titrant again will stay in the burette, but this time the peroxide will end up being where the sample is, and we will use the volume of titrant added to calculate the concentration of the peroxide. Now, in order to do this, we need to start by actually creating our primary standard. Now, to create the primary standard, it's important to remember that this is a solution preparation from solid. So I have my weighed out solid of iron 2 ammonium sulfate, and we have our prepared volumetric flask, but we remember that we can't pour the solid directly into the volumetric flask because the neck of the flask is too narrow and the solid could get stuck. So we will be using a funnel in the volumetric flask, but we need the solution to be poured into that flask. So we're going to start by pouring our solid into a transfer beaker and rinsing out what little bit of solid is left in the weigh boat with some water. But this titration is very important because the sample must be acidified. So we need to dissolve the iron 2 ammonium sulfate in 40 milliliters of 2 mole per liter sulfuric acid. So instead of just using water to begin the dissolving process here, the solution preparation, we're going to use 2 mole per liter sulfuric acid. And we're going to stir that up and make sure that the solid mostly dissolves as best as we can before beginning our transfer process into the volumetric flask. The iron 2 ammonium sulfate dissolves fairly readily, but a little bit of agitation and the warmth of my hand here will speed up the process. Don't want any large crystals to be stuck in the neck even with the funnel, or to be stuck in the funnel, so it's important to take a second to really stir and dissolve as much of the solid as possible. Once dissolved, we'll be using the concept of adhesion, and again pouring the solution, touching the stir rod into the funnel, prevents splashing. And now I begin my rinses. Remember, it's important to do at least 3 rinses, and in this case I'm going to be careful to wash down the sides of the flask or of the beaker to make sure that I get all of the solid that I may have missed. We're going to rinse the stir rod and the funnel at the same time by continually pouring against the stir rod down into the funnel. One more rinse. It is important to watch the flask itself not to overfill, because if we pass the line in the flask, we have to restart the preparation of the solution. So 3 rinses. Our beaker and our stir rod are now considered clean. Our funnel is considered clean. We'll place those off to the side. And now we just need to top up the volume to the line. It is important when filling to remember the neck fills much faster, and also to bring your eye level down to the level of the line in the flask to avoid parallax when reading the meniscus line in the flask. Once we have the volume, we take the cap, place it on the flask, and again, we'll invert 7 times in order to stir. We don't shake volumetric flasks because the air bubble can't actually leave the neck and it won't stir the solution properly. But if I just slowly invert and allow that air bubble to move, it effectively stirs the entire solution. Now, pouring 10 milliliter samples out of the volumetric flask is very difficult. So instead, we are in fact going to use the beaker that we just finished cleaning, and we're going to pour the primary standard into the beaker, allowing us to measure out 10 milliliter samples for our standardization. It's important whenever we decant into a beaker to label it. I have labeled this beaker with iron 2+ ions, but I will make that darker here using a blue Sharpie. So we can see there that we have iron 2 ions labeled on that beaker. We're now ready to go ahead and prepare our burette. Now, titration shouldn't occur until the burette has been rinsed. So we do need to take the burette out of our burette clamps. We need to make sure that it's rinsed. The reason for rinsing is, of course, not knowing who used the burette before or what chemicals possibly were inside the burette. We don't want any contamination with our titration, as this is a very accurate way of measuring a concentration. In order to rinse the burette, it's important to remember that a parallel stopcock is open and perpendicular is closed. This is very important, especially when titrating, to remember that if you go all the way around and it's still parallel, that's still open. So we close off the burette. We will add a little bit of water for our first rinse. We don't need a lot of water. We really only need about 5 milliliters of water at the bottom of the burette there. And then what we do is we allow the water to be tilted inside the burette, being careful not to pour it out the back end of the burette. And as I tilt it, I'm rotating the burette so as to rinse all the sides of the burette. When we're done with that, we will pour it into a waste beaker. We allow it to run through the tip to rinse the tip as well. And this waste beaker will be set aside to use whenever we need and be discarded in the end of the lab properly. Now, when the rinse is done, there will be a little bit of water left in the tip. And if I just went ahead and titrated, leaving a little bit of that water left in the tip, the very first amount of titrant added will be slightly diluted because of that. So the second step here is to do a titration rinse with the titrant. So we're going to close it off again, perpendicular. We're going to gather our titrant. And in this case, because the permanganate is not in a squeeze bottle, we'll be using a small burette funnel in order to fill up our burette. Now, we don't want to fill our burette, we only want to add a little bit of volume in order to do our rinse. In this case, it will be easier to see the rinse because the permanganate is purple. So now, same idea. I will tilt that permanganate, again being careful not to lose it out the back end of the flask or of the burette. And as I tilt, I rotate the burette, rinsing all the sides of the burette along the way. When I'm done, to get rid of that water, I'm going to run my titrant right through the tip as well, and that's going to fill the tip with titrant now instead of with water. So this allows my very first volume addition to be of titrant and not of diluted titrant. You can see that titration is a slower process, as this is fully open and this drains at a very set rate. You can't make it drain any faster. So you need to make sure not to rinse with too much, otherwise you'll be draining for quite a long time. Now, when the drain is complete, you will see there is a little bit of titrant left in the tip. This is a good thing because the volume of the burette is actually calibrated to include that little bit of titrant in the tip. Now I'm going to close off the stopcock, and now we are going to actually fill the burette with titrant because we don't know how much titrant is required for the titrations. It's important not to worry about filling exactly to 0 because a titration involves recording the initial volume and the final volume. And at times, students try desperately to get it to 0 and they overfill their burette and spill everywhere. So now we have a burette full of titrates. I'm actually going to start by running a little bit into the actual tip to fill it up, such as that, so that I have no air bubbles when I'm trying to titrate my actual samples. In this case now, we can see the initial volume inside that burette. And what we can see here when we take a look at the volume, we can see that the top of the bubble is actually at about the 5.9 mark. Now take a look, it is very important to read a burette properly. The 5 milliliter mark is up here and the 6 milliliter mark is down here. So a burette is like a graduated cylinder upside down. So the volume actually increases as you go down. So the top of the bubble seems to be at this 5.9 mark, but the bottom of the bubble, the bottom of the meniscus, the dark spot there, is right at the 6.0 mark. And it is important to use 1 decimal point in noting volumes because this burette is set to 1 decimal point. For the remainder of the lab, I will verbally read the meniscus so as to avoid the difficulty of focusing. But remember that to fully achieve the accuracy required in titration, it is important to record right to the bottom of that meniscus. And then we place a burette into our clamps. And we are effectively ready to titrate. Now our sample size is 10 milliliters. So we're going to use our graduated cylinder to measure out 10 milliliters. In a very accurate titration, it would be important to use a pipette to measure out a sample. And measuring with a pipette is called taking an aliquot of the sample. But in our case, we're just going to use our graduated cylinder to simplify it. And then we're going to go ahead and titrate our sample. To titrate, there are several methods, and it really depends on your comfort level. I am right-handed, and so I want to be able to swirl my flask with my right hand because I have more control over that hand. And what I'll do is I'll operate the stopcock with my left hand. However, some people are perhaps more comfortable the other way, and you will swirl with your left hand and you'll operate the stopcock with your right hand. You can turn the burette around. It really does not matter if you can read the numbers at this point. You wait until you've reached the end point, which is the color change that indicates the equivalence point of the reaction. Try to remember that. End point is only a color change or an indicator that you've reached equivalence point. And equivalence point, of course, is when the moles of the sample are equal in mole ratio to the moles of the titrant that you've added in. I have also seen people cross over and titrate across the burette like that, and then swirl with your left hand. Again, this entirely is up to you and your comfort level. I will leave it as this. We need to measure out 10 milliliter samples, and it's very important again to use the meniscus. And because it's often hard to get it exactly on 10 using the beaker, we use an eyedropper to remove or add volume as required. Once we have exactly 10 milliliters, we pour that into our Erlenmeyer flask. And we're prepared to titrate. Now when titrating, it's very, very important to get the tip past the neck of the Erlenmeyer flask because that's what prevents spilling. It's also important to have a white piece of paper underneath when observing color changes because this color change will go from colorless, and what we see here, to a pink color. Not the purple of the permanganate, but a very light shade of pink. And the ideal volume added will finish on a single drop or even a half a drop. You can see if I drip in, now that we've recorded our initial volume of 6.0, if I drip in a little bit of titrant, it fades immediately. What this shows is that we're nowhere near the equivalence point of the reaction. So again, we'll show that dripped in and how it fades. Now, it's really important not to just drip like this and then look and drip and look. We have to make sure that we're titrating properly, which includes holding the flask, and I raise mine slightly off of the surface, and I swirl. And for my very first titration here, I want to get used to controlling the flow rate to see if I can't produce a drip pattern that is very slow and controllable. Because as I get closer to the equivalence point, the amount of titrant required to change the color will be very, very small. So I need to practice a slow drip, perhaps a faster drip, such as that. And once I have my first equivalence volume, my second and third trials, or if I need more, my fourth and fifth trials, I can actually very quickly open the stopcock for most of the volume and then shut the stopcock off and drip only the last half a milliliter or so. Because this is my first trial, I have no idea what the equivalence volume will be. If we take a look inside the flask, as I'm swirling, the color is fading fairly quickly, so I know that I'm still not too close to the equivalence point. However, I don't want to rush the titration and miss that equivalence point. So I will try and do a quicker drip pattern. There we go. And observe how long it takes the color to fade. And I can see the color is staying around a little bit longer now. So I'll slow the drip pattern down. And we'll continue to swirl. It's very important to continue to swirl because the swirling keeps all of the moles of the reactants mixing. So now I've slowed down my drip pattern. And we'll continue at this rate for a while until I notice that the color takes even longer to fade, in which case I'll slow it down even more. The first trial is very slow because, again, we don't know the equivalence volume, so we're not sure how much titrant we need to add. And unfortunately, in titrations, the color change happens very, very quickly. And 1 or 2 drops can be the difference between before the equivalence point and after the equivalence point. And the color is still fading fairly well. Some titrations could take several milliliters, 10, 20, 30 milliliters. However, for the purposes of high school labs, we tend to keep the volumes relatively low so as to be able to do several trials in one burette of titrant. Very important to continue to swirl. And if perchance a small drop touches the side of the flask, what I can do is use a wash bottle and just rinse the drop into the actual mixture. I need to rinse any drops that have exited the burette into the mixture because that could be the difference in reaching the equivalence point. You cannot use water when doing a pH titration because water will dilute. And once you dilute, the concentration of hydronium ions will be lower, and that effectively changes the pH. However, in a redox titration, the moles of the sample are set once I measured out my 10 milliliters, and adding water will not change the number of moles that are reacting. I can see the color is taking a little bit longer to fade, which is a good sign that we are approaching our equivalence point. And a good end point is when a single drop or a half a drop can leave that flask a completely different color. And what we're looking for here is a very, very light shade of pink. You can see the color does stay in the flask quite a bit now, even while swirling. So we are getting closer to the equivalence point. It's important not to worry about the volume and try to watch the volume on the burette while titrating. The only thing that matters right now is continuing to swirl, being ready to shut off that stopcock, and watching for that color change. Because when that color change happens, it's very important to shut off the stopcock. So I've actually slowed the drip rate down even a little bit more because I can see that color is almost not fading at all. And there is our endpoint. Now it could be difficult to see, and so what we can do is we can prepare our second trial and compare the color of the sample to the color that we've just reached using our titration. So here we have untitrated sample compared to our endpoint, and we can definitely see that there is a slight pink color. Now we go ahead and record the volume from the burette. And in this case, the burette is exactly at 20.0 milliliters. So our initial volume was 6.0 milliliters. And our final volume is 20.0 milliliters. This is very important to write in your data table. So initial volume of 6.0 milliliters and final volume of 20.0 milliliters. Record that in your data table for the first trial of your standardization of potassium permanganate using acidified iron 2 ammonium sulfate solution. We're going to go ahead and move that sample, bring in our second sample, and what we know now is the initial volume for this titration will be the final volume from the last titration. So the initial volume is going to be 20.0 milliliters, and I'm actually also fairly sure that it takes about 14 milliliters in order to react to endpoint, to equivalence point. So what I'm going to do is I'm going to be swirling, but I'm going to open the stopcock fully, and I'm actually going to watch the volume in the burette. 14 milliliters from now will be at 34 milliliters, so I'm going to stop it at about 33 milliliters and then finish off the titration slowly for the last bit. Very important here to swirl, because if we don't swirl, then what happens is that a reaction can be, or a secondary reaction can occur where the titrant is entering into the sample, and I can't allow any other reactions than the redox reaction that I want here. So we're reaching the 10 milliliter mark here. And we're going to keep going until we get very close here to about a milliliter away. And now what I can do is I can slow back down to my drip pattern. And this will take a lot less time in order to get to our equivalence point because we've already added in the majority of the volume required. Now this isn't to say it will be exactly 14.0 milliliters added like it was the last trial. However, we do know it should be near 14, and we've gotten the solution much closer to that. Again, now I'm not caring about the actual volumes, I'm caring only about the color, and I'm watching the time it takes for that color to fade. And I can see that we are indeed close, not that close quite yet, but very close. And if we get a little closer, we'll try and actually stop it on a half a drop, just to demonstrate the idea that it does not take a lot of titrant to change the solution color once we get to the equivalence point. So I am dripping this very slowly, like I said, trying to aim for maybe being able to add a half a drop to reach the endpoint color that we need. One more drop. It is sort of a difficult way to guess or predict here how much it will take. I will suspect that maybe this last half drop could change the color. Now I can rinse that in with a little bit of water. So I see a small amount is hanging. That has to be counted as volume, so I'm going to rinse that in. And then I will swirl my flask. And I do indeed have a very slight pink hue. I think this will be very, very tough to see in the camera. It is not quite as dark as the first pink. Move my wash bottle, sorry. But I definitely do have a pink hue using just that half a drop of volume added. We'll go ahead and we'll read the burette. And in this case, we are again exactly at 34.0 milliliters. So we've reached 34.0 milliliters, which means that for the second trial, we have also exactly 14.0 milliliters added in. This does not usually happen for titrations, but it may, depending on your patience and your accuracy in measurement. We'll prepare our third trial because we need to get 3 trials within 0.1 milliliters in order to count it as a valid average. Now we realize that the volume added is about, well, so far exactly 14.0 milliliters. We have a certain volume left in the burette. We need to make sure that this volume is enough to perform one final trial. Otherwise, we need to refill the burette. Now, we're at 34 milliliters. If I add 14 milliliters to that, I'll get to 48. We have 50 ml burettes. So I do have enough to perform a third trial using this volume in the burette. So we are going to go ahead and start adding again straight out. We're going from 34, we're aiming for 48. I will slow down at the 47 milliliter mark and titrate the last milliliter slowly. As we're coming up here, we've reached the 10 milliliter mark right now. And we're approaching the 47 milliliter mark. So once I reach the 47 milliliter mark here, we're going to slow down the drip rate. And we're going to complete this last milliliter here at a more gentle drip rate. Still very important to keep swirling. Turn the gradations away there so we can see. And that is our end point. Now there is a small amount still hanging. I do need to rinse that off. It has been considered added volume, so I will be a slight amount overshot, but not enough to hopefully make a difference in our trials. So we're going to lift up our burette and take away our samples and prepare for our next titration. In this case, our final volume is 48.1 milliliters. 48.1 milliliters. So we can see that we have had a slight increase in the amount added, but our 3 trials are within 0.01, which allows us to go ahead and do an average calculation. Our burette must be filled because to do our next titration, our burette has to be topped up because we don't know the volume required. for the titration of the peroxide. So again, we'll use our small little burette funnel. And if you're tall enough that you can fill the burette as it is in the stand, that simplifies taking the burette off. Again, not important to go to zero. So in this case here, we have our burette volume to be at 6.5 milliliters. Now we need to prepare our sample for our peroxide. Now our peroxide requires acidification. The peroxide does not react with the permanganate unless the permanganate is acidified. However, we cannot acidify the permanganate because once the permanganate is acidified, it is such a strong oxidizing agent, it will in fact react with the water that's part of its own solution. So we can't allow that to happen. So our peroxide, we will measure out 10 milliliters. Again, being very careful to get this right on our meniscus. So we'll use our eyedropper to remove excess peroxide. Get that meniscus right to 10 mils. Take away our iron sample, which we've done. And now, in order to make this react, we actually also have to add 5 milliliters of acid. So that 2 mole per liter sulfuric acid, we need to make sure to add 5 milliliters to each one of our trials. Now in this case, if the meniscus is not exactly at 5, it is not a problem because the reaction is using acid as an excess reagent. It's the peroxide that needs to be exactly 10 milliliters. So now we have our first peroxide titration. We'll zoom this back in. The endpoint that we're looking for is the same endpoint as it was in the iron solution. We're ready here with our initial volume to be 6.5 milliliters. And then we will go ahead and perform the same titration as we did the very first titration from the iron, which involves a slow drip pattern. Very slow drip pattern here. Try that again. In order to reach the end point without an overshoot. We're really not sure how much it will take. We can see that the color does not fade as quickly as it did for the iron reaction. So make sure to swirl this really, really well, as it does not appear it will take a lot to reach our endpoint. It is important to have two data tables ready to record results. The first data table was the standardization of the permanganate using acidified iron 2 ammonium sulfate. The second data table we should have here is now the titration of acidified peroxide, and we could even say acidified diluted peroxide, as the hydrogen peroxide was diluted 40 times before beginning the titration. So the titration of acidified diluted hydrogen peroxide with potassium permanganate. And the concentration of the permanganate will be determined from calculations from the standardization. Again, not caring about the volume, only caring about the color change, so that we can see how close to our endpoint we are. That color definitely is staying around a little bit longer, so we are getting close. Very important to swirl. Without swirling, the solution may look pink until you swirl it, and some of the peroxide does react with the permanganate and the color fades. So it's very important to swirl. And in our case here, to find a pink endpoint, that white piece of paper underneath is very essential, as on black we would not really see a change from colorless to pink. The color is very slow to fade. I believe us to be close to our equivalence point. We'll try to go at a drop at a time here. And you can see the color is very slow to fade. Maybe 1 or 2 drops more. Oh, maybe a few more. So long as I swirl, I'm mixing my reactants very carefully, and that allows us to make sure that when we've reached equivalence point, all the moles of the reactants have reacted. You can see how slowly that color fades. Must be very soon here. Reaching endpoint is a little different with the peroxide as the iron, as the way this fades is slightly different than the iron reaction, and this whole solution changes pink and then fades after a few swirls. The iron turned pink and stayed pink. But it is important to take time and not to rush a titration, because once you've overshot, that trial may not be included in average calculations. So even though this may seem slow, it does help to not have to do a 4th or 5th trial in order to deal with an overshoot. Solution very slow to fade. Very slow to fade. Oh, it did fade. So we are within a drop, I suspect, here, or half a drop. So we'll try to add a partial drop to see if we can't get right to our endpoint. So there's a full drop, and it is remaining pink. Very, very faint pink. Again, might be difficult to see. The easiest technique would be to create our next sample, and that way we can compare to our untitrated color, which would be colorless in this case. And again, we can see that the endpoint is definitely slightly pink compared to the colorless untitrated sample. So we go ahead and check our burette, and in this case we can see that the volume is at 15.7 milliliters. 15.7 milliliters. So our initial volume of 6.5 milliliters, our final volume at 15.7 milliliters. Taking a look at that, we can see that it is not quite 10 milliliters. In fact, it's just over 9.2. So we're going to take our second trial here, as our starting volume is 15.7, and we're going to add in very quickly about 8.5 milliliters, bringing us to 24.2 milliliters, and then we can slow down the remaining parts of the titration. Very important to swirl. I'm sure you could see right at the start the flask went completely pink, but once I swirl, the color will fade. Now we're at the 24 milliliter mark. We're going to slow down again to drop by drop, reaching end point without overshooting. I'm swirling a little more vigorously here as my drops are coming in a little faster, helping us make sure to mix very, very well. Now I can see that part of my swirling has placed some pink along the side of the flask. So this is very important to rinse all of the reactant into the flask and not to swirl too vigorously and have splashing occurring, which removes reactant from the actual mixture. I will slow down the very last few drops. Again, trying to achieve 3 trials within 0.1 milliliters of each other. Very close here. As we can see, the color does take some time to fade. Our last few drops here to reach our equivalence point. And then the average volume of the trials will be used to calculate the concentration of the peroxide. But it is important to remember the concentration is diluted 40 times. So the final concentration that is calculated must be multiplied by 40 in order to calculate the concentration that was in the bottle. And the pink is almost not fading. Within a few drops here, we should be at our end point. Suspect this last drop. And that last drop did fade, but I have a half a drop hanging. So if we add that little half a drop with some water and swirl, we get a pink color. So another half drop endpoint, allowing us to accurately get our volume here.